Welcome to the Explainer. Today, we're going to plug in and demystify the basics of electricity. I'm talking about the simple rules that power pretty much everything, from your phone all the way up to the entire power grid. All right, so here's the game plan for today. We're going to start with the big picture. What even is a circuit? Then we'll get to know the three main players: current, voltage, and resistance. And to wrap it all up, we'll look at the one beautiful law that connects everything.
Okay, first things first. We have to set the stage, right? Before we talk about what's actually moving, we need to get our heads around the system that makes it all happen. And that is the electric circuit.
So, what is a circuit really? Well, at its heart, it's just a closed loop. And it's designed to do one of two things. Either it's moving energy to get some work done, lighting a light bulb, spinning a motor, or it's moving information. And that's the foundation for, well, every computer and phone we use. And pretty much every circuit has three basic jobs to do. First, you've got a source, like a battery, that generates the power. It's turning, say, chemical energy into electrical energy. Then you've got conductors, your wires, that transport that energy from point A to point B. And finally, something has to use it, right? That's your light bulb or motor, turning that electricity back into something useful, like light or motion. Okay, so we know the circuit moves energy, but what is the stuff that's actually flowing through the wires? To figure that out, let's zoom in on our next big idea: electric current. The scientific way to say it is that current is the flow of electric charge. Just imagine these teeny tiny particles, and each one is carrying a little bit of electrical energy. Current is just a measure of how many of those particles flow past a certain point in a wire every single second. And the unit we use for that, it's the ampere, or as you've probably heard, amps. But here's the thing, this flow can't just happen anywhere. It needs a specific path. And that's where the idea of conductors and insulators comes in. Think of a conductor, like copper wire. It's basically a superhighway for electric charge, a wide open pipe that lets it flow with almost no effort. But an insulator, like the rubber coating on that wire, that's a total dead end. It's like a blocked pipe, and it stops the flow completely. And having both is absolutely crucial for making circuits that actually work and, are safe. Right, so we've got a flow, but stuff doesn't just flow for no reason, does it? Think about it. Water in a pipe needs pressure to move it. Well, in electricity, that push, that pressure, that's what we call voltage, and that's our next big concept. So yeah, voltage is exactly that. It's the electrical pressure that gets the charge moving in the first place. We measure it in volts, and what it really represents is the amount of energy, or push, that's available to move the charge from one spot to another. So, pretty simple. Higher voltage means a bigger push for every little bit of charge. Let's go back to that water pipe analogy because it works so well here. If current is how much water is flowing through the pipe, then voltage is the pressure pushing that water. It's the difference between a high-pressure fire hose and just a lazy trickle from a garden hose. More pressure, more voltage, mean you have the potential for a much stronger flow. Okay, so let's recap. We've got a push, which is voltage, and we've got a flow, which is current. But if you just have a massive push and a wide open flow, things can get out of hand, right? We need a way to control it. And that's where our gatekeeper comes in: resistance. And the number one tool we have for this job is a little component called a resistor. Whenever you look at a circuit diagram, you'll see this zigzag symbol. That's him. And his whole purpose in life? It's literally just to get in the way, to create a bit of a bottleneck and slow that current down. The name really says it all. Resistance is just a measure of how much something fights against the flow of current. You can kind of think of it like electrical friction. And we measure it in a unit called the ohm, which we write with that Greek letter omega. And this is what makes resistors so useful. Take a look at this graph. It shows what happens to the current as we increase the voltage. And what do you see? It's a perfectly straight line. What that tells us is that the relationship is super simple and predictable. If you double the push, the voltage, you get exactly double the flow, the current. It's that reliable. All right, so we have our three key players: the push, voltage; the flow, current; and the opposition, or the gatekeeper, resistance. Now for the magic part, let's see the one simple, elegant rule that ties them all together. So, what's the connection? How do these three things, voltage, current, and resistance, relate to each other? You might think it's something complicated, but it turns out to be one of the simplest and most beautiful relationships in all of physics.
And here it is, V equals R times I. This is Ohm's law, and I'm not exaggerating when I say this is one of the most fundamental equations in all of electronics. It just says that the voltage, the push, is equal to the resistance times the current.
And the power of this law is in its simplicity. I mean, really think about that. Because this relationship is so simple, so predictable. It's what allowed us to take electricity from being this weird, magical force of nature and turn it into the most powerful and controllable tool we've ever had as a species. Okay, let's put it to the test with a quick example. Let's say you've got a resistor, and its resistance is 2,000 ohms. Now, you apply a 12-volt battery across it. The question is, how much current is going to flow? Well, we can just rearrange Ohm's law a little bit. If V equals R times I, then I must equal V divided by R. So we take our 12 volts, divide by 2,000 ohms, and we get 0.006 amps. Or, to make it sound a bit cleaner, 6 milliamps. See? Perfectly predictable. No guesswork needed. And I really want to drive this home. This is not just some formula you memorize for a test. This is the rule book. It's what allows engineers to design literally every electronic device you own. It lets them predict exactly how a circuit is going to act before they even build it. It's the key to controlling electricity. So there you have it. It all boils down to a few simple ideas, doesn't it? A push, a flow, and something getting in the way. And it's all tied together by one incredibly simple law. That simple foundation is the bedrock of, well, our entire modern world. It really makes you wonder, right? Now that we know the rules of the game, what else can we build?